Welcome to the Deep Dive. We know you want to get straight to the important stuff, so today we're diving into something pretty exciting. We're talking about running those huge, powerful, large language models, the AI brains behind everything right on your own home computer, your laptop, maybe even your phone. Forget the giant cloud servers for a minute. We're looking at bringing that AI power home.
Exactly. It's been the case for a while that these really big models, billions of parameters, they needed massive data centers. But what's really shifted is this idea, this possibility of using the tech we already own, your laptop, your desktop, maybe an old tablet.
Yeah, it's a big challenge though, right? Pushing our everyday gadgets to their limits.
Definitely.
And we've got a great source for this discussion, a new paper called PRIMA.CPP, Speeding Up 70B Scale LLM Inference on Low-Resource Everyday Home Clusters. Just the title suggests something big is happening. They mention models like DeepSeek R1, QWQ32B, showing real potential on home devices.
It's the scale that's kind of mind-blowing. A 70 billion parameter model running locally, that would sounded like pure science fiction not long ago. It just shows how fast things are moving.
But as the paper points out pretty clearly, the way we do this now, running LLMs locally, it still needs some serious hardware.
Yeah.
Like high-end GPUs, loads of fast RAM or VRAM, stuff most of us just don't have scattered around the house. We're talking normal Wi-Fi, a mix of machines.
Yeah, the paper gives a really concrete example, running
Yeah.
Qwen 2.5, which is like 14 billion parameters, so
Yeah.
smaller than the huge ones on a Mac M1 with 8 gigs of RAM. It took something like 10 seconds just to generate one token, one word. Well, it's pretty slow. Not exactly a smooth conversation.
No kidding. So that brings us to PRIMA.CPP, this new system from the paper. It's designed specifically to tackle these limitations. And the claim is pretty bold. Running those giant 70B models on regular home devices, mixing CPU and GPU, even with not much RAM, over standard Wi-Fi.
And cross-platform, too, which is important. The real key with PRIMA.CPP, from what I gather, isn't just making it possible to run these models. It's about making it efficient, getting that latency down so it feels responsive, actually usable for things you might want to do at home.
Okay, let's unpack this. Our mission here is to figure out the magic behind PRIMA.CPP. How does it work? And, what does it mean for us having this kind of AI power locally? Maybe start with the basics. What's the current state of play? Why is it so hard right now?
Well, like the paper says, if you're trying this on your phone or a standard laptop without a beefy graphics card, you're pretty much stuck with smaller models. They mention like 7 billion parameter models for maybe some on-device translation, stuff in browsers, maybe 3.8 billion on Android. They're just more manageable for that kind of hardware, less demanding on memory and processing.
So there's this massive gap between the headline-grabbing 70V models and what you or I could actually run at home. And that 10-second per token example really drives home the bottleneck. It's painfully slow.
Totally. A single machine just hits a wall pretty fast, which naturally leads to the next idea. What if we could pool the resources? Use your laptop, plus that old desktop, maybe a tablet. Combine their power.
That makes intuitive sense. I've definitely got devices just sitting around. But I guess it's not that simple. The paper talks about existing ways people have tried this, distributed approaches.
Right. There have been attempts. Two main strategies, really. One is pipeline parallelism. Think of it like an assembly line. The model's broken into steps. Each device does one step, passes it on.
Okay.
The other is tensor parallelism, where the big chunks of math inside the model, the tensors get split up. Each device handles a piece.
Like a relay race, or
Yep.
splitting up a giant spreadsheet. Got
Yeah.
it. But the paper says these have drawbacks, especially for home users.
Yeah, they mention a system called EXO. It tries to assign model layers based on memory devices with more RAM get more layers, which sounds logical, right?
Yeah.
Avoid running out of memory. But the problem is that device with lots of memory might have a slower processor. So the actual computing becomes the bottleneck, like having a huge warehouse but only a tiny loading dock.
Okay. The memory-rich device becomes the slowpoke. What about assigning based on processing power then? Give the faster machines more work.
That's the other way, yeah. Give the heavy lifting to the powerful devices. But the risk there is you overload them with too many layers and they run out of memory. That OM error, out of memory. People have tried shifting layers around dynamically, but the paper suggests that can actually slow things down more if weaker devices end up doing too much work.
So it's like a catch-22. You're either bottlenecked by memory or by processing speed. And the paper also said a lot of these systems still need the total memory across all devices to be enough for the whole model. That's still a big ask for home setups.
Exactly. If your combined RAM and VRAM still have to hold the entire model, you're limited. Plus, many older systems didn't really use both the CPU and the GPU effectively on each machine, and they often skipped quantization that technique to shrink the model size, making the memory problem even worse.
Okay, challenge is clearly defined. So let's get to the good stuff. How does PRIMA.CPP tackle this? The paper lists 4 key features. First one, disk offloading. What's that about?
Disk offloading is pretty fundamental here. It basically means your cluster can run a model even if the total RAM and VRAM is less than the model size. The idea is if a device needs a piece of the model that's not in its fast memory, it pulls it quickly from the local SSD, the solid-state drive. This just breaks that constraint that everything must fit in memory. It lets you aim for much bigger models.
Okay, so bits of the model get swapped in from storage when needed. That sounds like it could unlock those huge models.
Sure.
But doesn't that just shift the bottleneck to the disk speed? SSDs are fast, but not RAM fast.
You're right. Disk I/O is definitely a potential bottleneck, absolutely. Which is why Prima.cpt doesn't just rely on disk offloading. It has other tricks up its sleeve to kind of hide that latency. We'll get to those.
Okay.
The second feature they mention is GPU and CPU offloading. How does that help?
That sounds like using all the parts of the computer better, right? Not just relying on the graphics card memory or the main system RAM separately. Prima.cpp can sort of shift work between them, making the resources more flexible.
Exactly that. It intelligently uses both the fast VRAM on the GPU and the larger pool of system RAM, and it can assign bits of the calculation to the CPU or the GPU, depending on what makes sense at that moment. It helps avoid that situation where, say, your powerful GPU is just sitting there idle while the CPU is struggling.
Makes sense. Use the right tool for the job inside each machine. Third feature, quantization support. Q4K and IQ1. We touched on this, but how does it shrink the models?
Quantization is basically about reducing the precision of the numbers the model uses internally, its weights. So instead of maybe a 32-bit number, you use a 4-bit one, that's the Q4 and Q4K, drastically fewer bits per weight, which means the whole model becomes much, much smaller. IQ1 is even more aggressive. Think of it like making a photo file smaller. You might lose a tiny, tiny bit of quality you barely notice, but the file size drops dramatically.
Right, putting the model on a diet, hopefully without making it dumb.
Yeah.
Okay. And the fourth feature, .map, for lazy loading and OS-managed caching. Sounds technical. What's the benefit?
Yeah, it's a system thing. It lets Prima.cpp map the model file directly from the disk into the program's sort of virtual workspace. The big win is lazy loading. The operating system only pulls the specific bits of the model from disk into actual RAM when they're really needed for a calculation. And the OS manages this RAM as a cache. So stuff you use often stays in RAM, stuff you haven't touched in a while can get automatically cleared out by the OS if something else needs the memory. It's like a smart librarian fetching only the exact pages you need right when you need them and managing the shelf space.
So map works hand in hand with that disk offloading. Makes it much more efficient because the OS handles a lot of the optimization. Okay, those are the core ingredients. Now, the paper talks about their specific strategy for spreading the work. Piped ring parallelism with prefetching. How does that work differently from standard pipeline parallelism?
Right, so standard pipeline is a chain, right? Piped ring connects the end back to the beginning, makes a loop. But the really key part in Prima.cpp isn't just the ring structure itself. It's that devices in the ring work together to predict a single token, potentially over multiple passes or rounds.
Multiple rounds for one word. Why do that?
It comes back to the limited memory on each device. By using what they call a smaller layer window size, meaning each device only handles a small chunk of the model's layers in each round, the memory needed at any one time on that device stays low. And this is super important to avoid something called the prefetch release effect.
Prefetch release. Sounds bad. What is it?
Yeah, the paper explains this well in the appendix. Imagine a device trying to be clever and loading model layers from its disk before they're needed. That's prefetching. Good idea, right?
Seems efficient.
But if it prefetches too much too fast and its memory is tight, the new layers it loads can actually kick out the layers it prefetched earlier, layers it needs for the very next step. So I have to go back and load those again from disk. Totally redundant I/O kills the benefit of prefetching, like carefully packing your car, then needing something at the bottom, unpacking everything, getting it, repacking. Super inefficient.
Ouch. Yeah, that sounds awful. So how does the layer window size in this piped ring thing avoid that?
By keeping that window small, Prima.cpp makes sure the amount of data being prefetched and held in memory doesn't exceed the device's capacity. It prevents that overwriting. And with the multiple rounds, each device does its small bit, passes the result on, gets the next bit for the next round. contributing to that single token prediction without ever blowing its memory budget. The paper even has diagrams showing how this makes prefetching, overlapping the disk, reads with the computing, much more effective.
Okay, that clicks. It's a more controlled, memory-friendly way to do the distribution and preloading. So the next big question is, which layers go to which device in this ring? This is where the layer-to-device assignment, or LDA problem, comes in, and their HALDA algorithm. Sounds like the brains of the operation.
Yeah, this is where it gets really sophisticated. The LDA problem is basically, how do you optimally spread out all the hundreds of layers in a big model across your mix of home devices? You've got different CPUs, GPUs, RAM amounts, disk speeds, even different operating systems managing memory differently. How do you slice up the model so the whole cluster generates tokens as fast as possible? It's a complex puzzle.
Sounds incredibly tricky. So many variables.
Exactly. The paper defines it formally, and they state it's NP hard, which, practically speaking, means finding the absolute perfect solution by checking every possibility would take forever. And there's that circular dependency issue, too. To know the best setup for one device, you kind of need to know the whole system's setup. But you can't know the whole system's best setup without knowing each device's best setup.
A real chicken and egg problem. So how does HALDA cut through that?
HALDA's pretty clever. First, it transforms that super hard NP hard problem into a series of more standard problems called integer linear programming, or ILP problems. It does this by considering different possibilities for the number of rounds in that piped ring, fix the number of rounds, and the optimization becomes something standard ILP solvers can handle.
Okay, breaking the big problem into smaller, solvable ones based on the number of rounds. What's the next step?
The second key idea is this iterative process. HALDA groups your devices based on things like OS Mac, Linux, Android, and whether they have enough RAM. It starts with a guess for these groups, solves the ILP for that grouping to get a layer assignment. Then, based on the result of that assignment, it checks if the devices are still in the right group. Maybe a device got more work than expected or less. So it adjusts the groupings, solves the ILP again, reevaluates, and it keeps doing this until the groups stabilize, until they don't change much iteration to iteration.
So it refines the assignment step by step until it settles on a really good distribution. And there was a calibration step for GPUs mentioned. What's that for?
Yeah, the calibration. That's specifically for cases where a powerful GPU might be underused. Maybe one device has a great GPU with free VRAM, but other devices are struggling, maybe even offloading work to their slow CPUs. HALDA has a rule. It can temporarily force the slowest, most overloaded device into the sufficient RAM category. This basically encourages the algorithm in the next iteration to try giving more layers to that underused GPU, hoping to balance the load better and speed things up overall.
That's smart, making sure the heavy hitters are actually pulling their weight. And they claim HALDA solves this in polynomial time. That's a big deal for an NP-hard problem.
It is. By transforming the problem and using this iterative approach with the calibration, HALDA finds a near-optimal assignment in a reasonable time frame. Makes it practical.
Okay, theory sounds solid. Disk offloading, CP-GPU use, quantization, map, piped ring, HALDA. Lots going on. But how does it actually perform? What did the experiment show?
They tested it on a pretty realistic home cluster. 2 laptops, a desktop, a phone. Crucially, only 37 gigs total RAM and VRAM combined. Not enough for a 70B model, even when quantized. They ran different sizes of the Llama model, 8B up to 70B, and compared PRIMA.CPP against Llama.CPP running on one machine, EXO, and Llama, other distributed systems. Measured things like token latency speed per word and time to first token, how fast it starts responding.
Did PRIMA.CPP deliver?
The results look pretty strong, yeah. For the bigger models like 30B and up, PRIMA.CPP was consistently faster on both metrics. For the huge 70B model, they saw token latency up to 15 times faster than trying to run it on the single desktop with Llama.CPP. And faster first responses, too. That's not just a little bit faster. It's a game changer for usability on home gear.
15 times.
Yeah.
Why did Llama.CPP struggle so much on the big models in their test?
Well, the paper explains that as the model got bigger, Llama.CPP just ran out of VRAM, then RAM on that single machine. Even though it uses a map, the OS had to constantly swap model parts in and out from the slower disk. That disk latency just killed the performance.
And what about the other distributed systems? EXO and Llama, what held them back?
They had issues too in this setup. EXO, assigning layers based on memory, gave too much work to a max metal GPU, which, in their test, wasn't as efficient as the NVIDIA GPUs in the other machines, creating a bottleneck. Llama, using tensor parallelism, got slowed down by the communication needed between devices, that all reduced step.
So PRIMA.CPP's strength seems to be that smart balancing act, using CPU and GPU on each machine while adapting to the different devices. Did they try other popular models too?
Yeah, they ran tests on QN 2.5, QWQ, DeepSeek R1 as well. The paper says the results were similarly encouraging, showing it's not just tuned for llama models.
They also did an ablation study, right?
Yeah,
Taking parts away to see their individual impact, like prefetching and Halda.
exactly. That study really showed how much each piece contributes. Prefetching gave a decent latency reduction, maybe 9–17% for bigger models, by overlapping disk reads and compute. But Halda, the scheduler, that was critical. Especially for the 70B model, it gave speedups of up to 30x compared to just assigning layers based on memory size.
30 times. Okay, so that intelligent assignment is absolutely key.
Definitely. It shows just how important getting that distribution right is when resources are tight. They also looked at the piped ring part itself. Seems it helps most when disk loading is really heavy, like for models bigger than 60B that really don't fit in memory.
Makes sense. So it's the whole package working together. Another thing they measured was memory pressure. Why does that matter for user experience?
Memory pressure is basically how much less available memory your computer has when the LLM is running. If it's really high, your whole system can slow down, other apps might lag or crash. You don't want running an AI to make your computer unusable for anything else.
Yeah, definitely not. How did PRIMA.CPP fare there?
It did well. PRIMA.CPP, like llama.cpp, kept memory pressure relatively low, mostly because they use mmap, keeping model weights in the OS page cache. That memory can be easily freed up by the OS if needed. EXO and Llama, on the other hand, kept more weights in active memory, leading to higher pressure, more risk of slowing down your system.
So PRIMA.CPP is faster and plays nicer with other things running on your computer. Good combo. Lastly, they talked about device selection and scaling. Do you need tons of devices? Does adding more always help?
Good questions. They found that because of the efficient disk swapping, especially with SSDs, you don't necessarily need enough total RAM to hold the whole model. That's a big plus. But importantly, just adding more devices isn't always better. If you add a really slow old device, maybe with a slow hard drive, it can actually become a bottleneck and slow the whole cluster down.
Ah, so the weakest link can drag everyone else down.
Pretty much. But what's cool is that the Halda algorithm in Prima.cpp can actually help identify those bottlenecks. It might suggest not using your slowest device to get the best overall performance from the cluster.
That's really useful, not just using everything, but using the right combination intelligently.
Exactly. It helps you figure out the best team to put on the field, so to speak.
Okay, let's wrap this up. What are the key takeaways from this deep dive into Prima.CPP?
I think the main thing is this looks like a really significant step towards running genuinely powerful LLMs, the 70B scale ones, on regular home hardware clusters. It does this through a combination of clever tricks, disk offloading, smart CPU GPU use, quantization, map, and crucially, that piped ring parallelism with the Halda scheduler coordinating everything across different devices.
And for people listening, what's the big potential here? What does this unlock?
Well, it really opens the door to having advanced AI running locally, on your own stuff, without needing a constant cloud connection. Think about more private, more customizable home assistants, or just making powerful AI tools more accessible to everyone, not just those who can afford massive cloud bills. Imagine an AI companion on your laptop that really understands you, but your data never leaves your house. That's the kind of thing this could enable down the line.
Of course, it's not perfect yet. The paper mentions limitations, right?
Yeah, they're upfront about that. Their tests use specific hardware, results might vary on different setups, and while it's much faster than other local methods, it's still probably going to be slower than running on optimized cloud servers. Plus, other apps running on your devices can still compete for resources and affect performance. Things to keep in mind.
Fair points. So as we finish, here's a final thought. Prima.CTP shows incredible progress in lowering the hardware barrier for powerful AI. What completely new kinds of AI applications could we see emerging in our homes soon, now that this kind of local processing power is becoming feasible? Go beyond chatbots. What else could become commonplace? Definitely something to chew on. And if you're technically inclined, the Prima.CPP code is open source on GitHub. We'll link it. Worth checking out. Thanks for joining us for this deep dive.